работы. Ну, как-то народ тянется, но тем не менее нам надо начинать уже работать, иначе мы выбьемся из расписания. Я просто хотел, вот сейчас листать, хотел немножко пару слов сказать про это все мы пропустим. Вот там есть расписание с сегодняшнего дня, дальше. Еще раз. Дальше, да. Ну, значит, вот сегодня план нашей работы. У нас сегодня 5 приглашенных докладов. Потом с кофе-брейком, значит, после нескольких докладов. Потом презентации ваши. Вот то, что мы называем презентацией в лифте. Это буквально 2 слайда, 1 минута. Просьба просто анонсировать, о чем ваша работа, и обратить внимание, у какого постера можно, номер постера, более детально с ней ознакомиться. После этого мы закончим до времени обеда, выйдем на крыльцо и сделаем групповое фото. Вот, поэтому там будет время для того, чтобы одеть куртки, чтобы не замерзнуть, и, значит, сфотографируемся. После этого обеда у вас есть вот эти вот талончики, которые вам дали во время регистрации. Обратите внимание, где вы обедаете, и если вы обедаете здесь, в академическом университете, там указано время, просто потому что здесь организовано обед в 2 смены, а те, кто обедают не здесь, а в политехническом университете, там, значит, уже никаких смен нету. Вот. Ну и времени достаточно, поэтому все вы успеете сделать. Потом постерная сессия и в конце некое подведение итогов, значит, награждение, закрытие. Вот такой наш план. Вот. И я с удовольствием представляю слово первому докладчику Алексею Акимову. Его доклад называется Ultra Fast Nanomechanics in Vertical Cavity Surface Emitting Lasers. Пожалуйста.
So good morning, ladies and gentlemen. First of all, I would like to thank organizers for inviting me to this very wonderful conference and, of course, beautiful city where I was born long ago. And it's very pleasant to see so many young and healthy and beautiful people here. And I wish, first of all the best for them in their career and studying physics. So I will tell about collaborative work. And this activity goes for many years, and you see here several institutions, universities from Germany, from UK, then from Joffre Institute, from Russia, and also from Ukraine. So there is a title, and first of all, before I just tell even introduction to our work, I will just tell several words about optomechanics, and because this is a very long topic, it is for many years, developed for many years, and the simplest prototype of this is, you see here, is a Fabry-Perot cavity, and one mirror is on the spring, and so this system has optical resonance. It may be many optical resonances due to the optical cavity, but it has also mechanical resonance, because you see the mirror is on the spring, so it has some frequency which is resonant for mechanical. And then the systems that traditionally they're classified as macro systems, and the frequency of the mechanical resonances are maybe from hertz to kilohertz, and these systems sometimes have a size of several kilometers, and say there is a huge interferometer which is used, several interferometers on our planet, which are used for detection of gravitational waves, and they were looking for them for many years, and eventually you all know that these gravitational waves were discovered and just confirmed the assumption of prediction of Einstein. If we go to very small sizes, to nanometers, then we go to much higher frequencies, to much higher frequencies. It may be megahertz, gigahertz. Usually it is realized by using some suspended nanostructures, some membranes, freestanding membranes, wires or cantilevers, and many beautiful works have been done during last decade. For instance, the researchers managed with these systems to go to quantum limit of the vibration, so they could measure one. It's like in optics, they measure photons, single photons. Now they measure single phonons, one phonon or two phonons. Also, they do with this optical cooling. So imagine you have some structure, and then you shine light on this, and this structure becomes to cool down. It's not a cold atom system. It's just cooling down. People go to 20 milli-K, just like this. So it is when energy of vibrations, these phonons are giving their energy to photons, and this is so cooling. But you may think about a lot of applications with this, but the limit for this is gigahertz, several gigahertz. Higher you cannot go. Recently, the idea to go to much higher frequencies is not, you cannot use suspended systems, you cannot use freestanding nanostructures, but there are some other solutions, and one of these solutions is just if those who work with semiconductor lasers, they know very well this. There is a cavity which is used for, say, vertical lasers, and so there is a space between two mirrors. These mirrors are made like distributed Bragg mirrors, which are called DBRs, I will call. And such systems have optical resonance. In this case, it is 1.4 electron volts, but these mirrors also are mirrors for phonons, for mechanical waves, and because it is due to the difference in acoustic impedances of the material from which these DBRs are made, and then the frequency goes to about 20 gigahertz, and you see, and this is the ground state, but if you may go to higher frequencies, to 100 gigahertz, and if you take if you make a cavity shorter, then you may go to terahertz even. So this is what we study, this is the systems we study, but we make one step forward. We put an active material here. So in a simple case, we take a laser. So we take a laser, there is active media which may laser, but we take a system which has a mechanical resonance and see what will actually happen. And on this topic, we started a bit less than 10 years ago, about 8 years ago. There are four parts. I don't have time to tell about all the parts. The first concerns lasers with quantum dots, vertical lasers. They all actually concern vertical surface emitting lasers, so-called VCSELs. And the first one concerns quantum dots in a planar microcavity. The second one concerns micropillars, electrically pumped micropillars with quantum dots. The third one is concerns optomechanical resonator with quantum wells, and the fourth work concerns probing the light for slow light field in complex photonic nanostructures, but the fourth one I shall not tell today. So this is the main object about which I will tell about. VCSEL, vertical cavity surface emitting laser. As I told you, there is a cavity, there is active layer, and there is two DBRs, which has optical resonance. It is for lasing, but it has also mechanical resonance. And to excite this resonance. Now we cannot excite it, it cannot be excited by itself. It's very interesting to have it just oscillating by itself, but we don't know how to do it yet. But we use strain pulse, and this is the first thing what I will tell about. So we need to create strain pulse. We need to start this vibration. So this technique is quite well developed during last 20 or 30 years even. Sometimes in a popular way we may say that it's ultra-fast hammer. If we kick something, you hear the sound. If we kick very fast, then the sound will be very high frequency. So how it is done? It is done with I will go back and again. So this pulse laser, optical pulse, hits metal film. Metal film expands due to heating. This is the simplest way, and then the strain pulse is injected into the crystal. The parameters of this strain pulse is quite well known now, and the typical one, I don't say this is in all the cases, it's about 20 nanometers width and several picoseconds long. It may be shorter, it may be less than 1 picosecond, but then you need to have some special methods to do this. So this pulse we shall inject into the laser and see what is happening. So the main mechanism, there are several mechanisms what actually this pulse may do, but the main mechanism, the most strong mechanism, is the impact of this pulse, strain pulse, on the active system. And this is why we use active system, because to increase this interaction between optical resonance and mechanical resonance. The basis of this goes to long ago to, it was revealed, the first effects of piezospectroscopic effects revealed by Gross and Kaplansky in 1960. And the idea is that if we have a strain, in this case stationary strain, and if we put it to the strain or stress, and if we put it to optical transition, then the energy of optical transition will change. Usually in the case of compression it will go up, usually in tension it goes down. And what is very good is that this is a strong effect. You don't need very high strain, gigapascals or something. If you have a strain which is 10 to minus 3, which is reliable to have in this picosecond pulse, then we get a shift about 10 millielectron volts, which is beyond the width of the optical resonance. So we may modulate the position of the overlap between optical resonance and the optical cavity. So let us again look how it will all go. So this is a VCSEL, our VCSEL quantum dots. So we excite these optically. In this part we excite them optically, and then these quantum dots emit light. And if we look from the side, then this is usual photoluminescence, not coherent, and it has broad spectrum. Due to the inhomogeneous distribution, there are different dots. Different dots have different emission, but emission from the front is very narrow. It goes only on the wavelength of the optical resonance. No mechanical resonance yet. It is not excited yet. So this strain pulse comes. This starts we call it shaking. It starts to shake this microcavity. And the main mechanisms, as I told, is just to move this overlap, to change the overlap between the quantum dot emission and the cavity resonance. So what will happen? And we measure this is I show what we actually measure. So again, microcavity VCSEL, Then the substrate, there is aluminum film to excite the strain pulse, and we detect it with 3-camera and spectrometer. So what will happen? Let us see. So the pulse comes, optical pulse comes, it generates strain pulse, just this pulse, more or less what I showed you earlier. Then it propagates through the substrate. The shape changes. I shall not go into details. It becomes more complicated, but it is well known, it is very well modeled, and it may be measured. Then it goes through the DBR. Again, the shape changes because due to multiple reflection on these layers. So then next it goes through the active layers. Something should happen with the emission, and then it goes back, and again the reflected pulse changes emission. Let us see what is the effect. This is the main result here. Very important that this is emission, not the difference in emission. Emission. So the baseline is not zero, it is unity. And then you see here it's 20, and then there is 50. So intensity increases 20 times. And when the reflected pulse goes, it increases 50 times. Huge effect. One would say, okay, that's perhaps on the threshold. Yes, on the threshold, the system is not very stable, whatever may happen. Yes, in this case, it is on the threshold. This is the effect of the threshold, and then I show here incident pulse and then reflected. But if I go above the threshold, okay, the effect is smaller, but still increase modulation of intensity more than 10 times on such time scale, external modulation. It's not mode locking where you just put the cavity and it is just going by itself. It is actually, personally me, I don't know well-developed methods to do this. Then if we go to saturation regime where the lasing is very stable, it goes less, but still it is the increase 5 times modulation on a picosecond time scale. The details depend all on how this distribution of quantum dots overlapping with photon resonance, with the optical resonance of the cavity. And in some cases, it's very interesting case. You see there is the case when it is just photon resonance is at the maximum of the quantum dot luminescence of quantum dot transitions. You see this sharp and very intense increase, and then you see oscillation. These oscillations is what I told you earlier. It's just the resonance, the resonant frequency of the cavity. Just if we go into the beginning of our prototype, it is the resonance of this spring, just a mirror on the spring. But this is a bit more complicated than just a mirror on the spring. So, why it is happening? What is mechanisms? There are actually mostly 2 mechanisms, but the most interesting is that it is there is some cooking analogy with this. So, if we have a sieve, if we put a flour, if you don't shake it, the flour will not go. But if you shake it, then the flour goes. So what is actually going from the point of without flour and without seed? So you see, only quantum dots, which are in the resonance with the cavity, they emit a photon, and it is coherent emission, a lasing emission. All other All other excitations, well, they are stuck there because they cannot emit light. They can emit only through the side, but it takes a long time. And now we start shaking it, and it is going to one side, and then all this what is stored is just going emit photons. Sorry, and then we see the increase of the emission. So this is the first part. The second part also concerns optomechanical resonance. The system is a bit different. It is you see micropillars. It is just like this posts with the DBRs and quantum dots, and it is electrically pumped, because earlier I told about optically pumped laser. So what is happening if we put again this strained pulse there? And you see the pictures from the street camera. They're a bit different, but anyway, in both you see that the wavelength of emission and the intensity, it is modulated with some frequency. The interesting fact is that there are two types of these micropillars. Some vibrating, modulation is going on a low frequency, less than 1 gigahertz, and another is higher frequency. If we look at modulation of intensity, you see again these red curves and black curves have different modulation frequency. They have different spectrum, if we take a Fourier spectrum from them. Why it is so? There are only two versions. There are no more. The reason for this is that there are these mechanical vibrations, and this micropillar has two main modes. One mode is just changing the length. This is called extensional mode, quite low frequency mode. Another mode is changing the diameter of this mode. This is more high frequency mode. And the question is whether we may excite both modes or not. Extensional modes may be excited with no problem, whatever happening, but this breathing mode may be excited only if you don't have a very good contact with environment, and environment is some special polymer. If this polymer is very good, has a very good contact with this micropillar, this mode will not be excited, or at least it will be excited very, very slightly. And if this contact is bad, then you will have this modulation. So this is the way how to probe this contact. I don't know any other technique which may probe this mode, this contact, to say perhaps TEM you may do this, but it is, first of all, it is very difficult, and then after that you cannot use the laser. But in this way, if you find that there is good contact or bad contact, whatever you need, you may use the same laser.